Let's look at this example problem to see how to involve work in this conservation of energy concept. So what work does is work adds or removes energy from our system. So instead of just having, say, kinetic energy equal to potential energy, now we'll have work to change the total energy. So we'll start the problem off with some kind of energy to begin with, and that's its total energy. And then we'll either add or subtract energy, and that'll equal the final energy. When we add or subtract energy, we don't call it add or subtract energy, and we don't call it the change in energy. Physicists call it work. So work is really their fancy way of saying the change in energy. Okay, let's look at this example problem to see what I mean. At the bottom, I've got a ball that's traveling at 5 meters per second. The ball has a mass of 2 kilograms, and the ball is going to climb 2 meters, and then at the top, it's going to have some unknown speed. But I have two forces acting on this ball. One of the forces is going to be here. Let's see if I can highlight this a little bit better. It's going to be there. So that's going to act against the ball, so that will remove energy from the starting energy of the ball. And the second force is going to be here, and that is going to add energy to the ball because it's going with the motion of the ball. So it's going to add energy compared to the beginning. So what I do in this, previously what I would do is I would say sum of the energy at the beginning. So let's say sum of the energy, in this case, let's call it the bottom. And then I would say equals the energy at the top. But now I've got these outside forces, whatever this 50 newtons is that acts for 1 meter, and whatever the 200 newton force is that acts for 2 meters. So I've got these forces I've got to deal with. All right, the 50-meter force is going to go the opposite direction of the motion. So the ball is going in this direction here. This force goes the opposite direction, so it's going to remove energy from the starting point. So what I'm going to write down here is minus work, and I don't have any other way of labeling this, so I'm just going to call it 50 just to label it. And then as the ball goes up the incline, the ball is going up the incline. It's my assumption it's going to continue upwards. And I've got this 200 newton force for 2 meters, and it's going the same direction the ball is. So what that's going to do is that's going to add energy, so we say plus work. Plus W, and I'll subscript 200 because I don't know how else to identify it. And I don't have any other outside forces, so that will be equal to the total energy at the top. And then when I look at this and break it down, I break it down the same way I did before. And by break it down, I mean insert my basic energies. So when I look at this, I'm going to say kinetic energy at the start, which is at the bottom, plus potential energy due to gravity at the bottom, minus the work of the 50 newton force, plus the work of the 200 newton force. And that's going to equal the kinetic energy at the top, plus the potential energy at the top. And then what I'm going to do is I'm going to go through my usual set of questions for my kinetic and potential energy to figure out which of these I have and don't have. At the bottom, is it moving? And the answer is yes, so I'll keep that energy. At the bottom, is it above the location's height? No, it's the height 0. That's going to go away. The works I won't do anything with. At the top, is it moving? We think so. And the potential energy at the top, is it higher than the other location? And it is, so I'll keep that. All right, that's great. Now that means that I got to write my equations out. 1 half mv squared minus the work of the 50. Whoops, let's undo that. That's going to be F50d for the 50 plus whatever the force is here times the distance of that 200 Newton force. And that equals 1 half mv squared at the top plus mgh at the top. Usually I tell you to isolate the variables before putting in the unknowns, but right now I'm going to tell you that you can take a shortcut here or make it a little bit easier for you. Throw in your numbers and units and then suppress the units and do the math. So I'm going to go ahead and do that. Notice that I cannot divide out the mass because if I look at this, FD, these two FDs, there's no M in those expressions. So I can't take out the mass. So the mass has got to stay there this time. Okay, let's start over here. Whoops. Got to change my pen. Here we go. Start over here. 1 half mass, 2 kilograms, times the velocity squared, 5 meters per second squared, minus 50 newtons, times the distance, which in this case, the distance is 1 meter. So I'll do that. 1 meter plus 200 newtons times its distance, and that distance is there, it's 2 meters. So that'll be 2 meters. And that equals 1/2 2 kilograms times my unknown at the top plus 2 kilograms times 9.8 meters per second squared times 2 meters. Awesome. Okay, let's see. Next, it's easier for me if I just get rid of some of the units here. So I'm going to rewrite this without the units this time. So that's going to be 1/2 2 times 5 meters per second squared. Well, I know that's 25, so I'm going to go ahead and write that out. Minus, I'll do a little bit of math along the way, 50 newtons in 1 meter. That's 50. I'm not doing too much math because I just want to do one, kind of keep it simple here. Plus 200 times 2, get rid of the units here. 400, that equals 1/2 times 2, that's just 1 times v squared, so that'll be v squared plus 2 times 9.8 times 2 again, so get rid of the unit. So 2 times 9.8 times 2, that's going to be 4 times 9.8, and 4 times 9.8. So I'm just going to go ahead and write what that equals. That's 39.2. So I'm trying not to do too much math at once while I'm suppressing the units because I don't want to get lost in it all. But over here I can see that the 2 times 2, that's going to go away, leaving just 25. So I'll stick with that. So now I've got 25 minus 50. So 25 minus 50 is negative 25 plus 400. So that's going to be 375 is equal to v squared plus 39.2. So v is equal to square root of 375 plus 39.2. And let's see. I don't know what that answer is. .32 meters per second. All right. So hopefully you can see how the work is handled in this kind of problem. So when I'm looking at this, I can see that when the work, force times distance, is the opposite direction of motion, I remove energy. When force times distance, the work is in the same direction of the motion, I add energy. Let's try one more example problem. So in this example problem, I've got a bow and arrow, and I'm going to shoot this arrow that's 0.1 kilograms until it gets to its highest height, and I want to know what the highest height is. So in order to do this, I need to find 2 locations to compare where I know the height and the velocity. One location will be here at the very bottom. The other location will be up here at the very top. So those will be my 2 locations, and the reason why I picked the top is because I knew at the highest height, well, that occurs when the velocity is equal to 0. And of course, at the bottom, well, that's easy. When we want to pull back a bow, I know that that is going to be at rest, and that is the lowest height, so that'll be pretty straightforward. All right, so now let's figure out this problem. I need to sum up my energies, just like I did before, so I'll start with that. All right, so that'll be sum of the energy at the bottom, because that'll be my starting energy. And then I either add or subtract work. What happens here is I got a force that's going up, and I've got a displacement that's also going up. So because the two go in the same direction, that's going to add energy to my arrow, which kind of makes sense, plus the work of the bow, and that's going to equal the total energy at the highest point. And remember, the word for the highest point is apogee, because apogee means the farthest away, and that's when the arrow is the farthest away from the ground. So that's our apogee. All right, then I'll define what energies I'm looking at. That'll be kinetic energy plus potential energy due to gravity plus the work of the bow equals kinetic energy plus potential energy due to gravity. Then I'll go through my questions. At the bottom, is it moving? No, think about it. When I pull the bow back, I'm holding it in my hand still, so that is actually going to go away. Is it at the is it higher than the other location? It is not higher than the other location. That goes away. At the highest point, let's see, work I don't do anything with. At the highest point, is it moving? No, because that's the definition of apogee and the highest point. So that goes away. Wow, this gets real easy fast. And that's equal to potential energy. All right, so let's look at our formulas here. That means I have the force of the bow times its distance equals mgh. Ooh, this would be nice. So I'm looking for the height. This is so simple. Actually, I could just isolate it with the variables instead of putting in the numbers right now. So h is equal to fd divided by mg. Well, I like that, simple. Okay, fd, let's see. So that's going to be 50 newtons times I pulled the bow back 1.5 meters, long arms, divided by the mass of the arrow, 0.1 kilograms, times g, 9.80 meters per second squared. And then when I actually do the math, I get a height of 76.5 meters. Okay, well that makes sense because all the energy in the bow that's putting into the system is going into the arrow to give it its maximum height where it reaches a speed or a final speed of 0. A student lifts a bucket with a 98 Newton force in 30 seconds out of the well at a constant velocity. If the bucket is lifted at 30 meters, then how much work is done on the bucket by the student? How much power is exerted by the student in watts and horsepower? All right, let's start with what do I know? Listing our givens. So our givens. What I know is that the weight of the bucket, which is equal to mg, is equal to 98 newtons. All right, that's right here. I know the time is 30 seconds. So 30 seconds. Moves at a constant velocity. That's important. That means the force it takes to lift the bucket is equal to the weight of the bucket. So 98 newtons is not only the weight, but it's also the force that's used to lift it because it moves at a constant velocity. If the bucket is lifted 30 meters, all right, so there's a distance that it moves. It's 30 meters. How much work is done? All right, so if I think about this, I'm going to have this bucket, and the bucket's lifted up, and it's lifted up 30 meters, and the bucket is 98 newtons. Since it's moved at constant speed, that's the force it takes to lift it up, is 98 newtons. And that is the distance. Well, that's great. So for part A, to find the work, I know work is the component of force parallel to displacement times the displacement. So the work is equal to 98 newtons times my distance, which is 30 meters. So that means that the work is equal to 2,940 joules. Okay, so that's part A, that's the work. How much power is exerted by the student in watts and horsepower? All right, so for part B, I know power is the change in energy over time, which is what we call the work. So that's work over time. The work I have, now I got to find the time. So to find the time, if I look at this, that's just going to be the 30 seconds. So that'll be easy then. So the power is equal to the work, 2940 joules, divided by 30 seconds. So that means the power is going to be 98 watts. Awesome. Now I got to convert that to horsepower. So horsepower is our bizarre unit of power. We know that 1 horsepower is equal to 746 watts. So that means to convert this, what I'll do is I'll take 98 watts, and then I'll use dimensional analysis basically. Horsepower over 746 watts, and that's going to equal 0.131 horsepower.